Semiconductor electronics. This is where actually electricity is applied. Okay, all that ECE 209 stuff, great, really important. But it's not really cool until you can start switching things and it can happen automatically. And you can turn power on, turn power off, and that's what we're going to learn today. Before we get started, however, 1 week from today, you owe me your description of your experiment. Okay? I want 1 paragraph per group. I wanted to tell me what the experiment is, and equipment you may need, and what you intend to learn. Grammar, punctualization, and grammar, capitalization, and punctuation are all count. Okay, guys. I was fortunate enough to already get one of them. Okay, and I read it and I went, what is this? Okay, so let's talk about audience. I want you to imagine you're writing this for your mother. Okay? If at the end of the day you read this and say, my mom would understand what I'm trying to achieve, what I need, and what I'm going to get out of it, then chances are I will. Okay? I don't have a clue what you're doing. I know there's a bunch of windmill projects, I know there's a bunch of airplane and drone projects, but I don't really have a clue about what your actual mission is, okay? So remember that about your audience. Always, always, always consider your audience when you're writing any work. Okay, nobody has asked me yet, what do I have available? What kind of toys do I have to play with to accomplish my experiment? Okay, I have Arduinos, I've got photosensors, I've got a pyranometer if you want to calibrate like a photocell to solar radiation so that you can change some digital number into an actual watts per meter square. We can do that. I've got BF350 strain gauges. These are just real, typical, ordinary, axial strain kind of gauges. But they work really nice. I've got strain gauge amps, weights. I've got the Instrong load frame, thermistors, oscilloscopes, power meters. I've got a lot of toys. So if you're wondering, do I have all this stuff to accomplish whatever you want to test? Okay, come see me. Excuse me. Okay, we're going to start off super simple. Probably the simplest semiconductor device is the diode. And we could get into all kinds of cool theoretical physics of why this thing works. Guys, all you need to know, it's a checker valve. Okay, one-way valve. It lets current go one way, but not the other. So the way these things are made is you've got 2 chunks of silicon. They are doped with, so one side has an electron donor, even I have to read this, such as arsenic, that creates your N-type layer. And when we talk about doping, we're talking about like 1 atom in a million, 1 atom in a million. Okay, really, really low concentrations, but it's absolutely enough. So with an N-type layer, you will have an extra electron in your outer valence shell. The other side, the other chunk of silicon, is doped with something like aluminum. That creates your P-type. Then these things are fused together and they create something called a p-n junction. When current goes in the forward direction, in the direction of the arrowhead, so your current goes that way, positive to negative, in positive current convention, pretty much nothing happens. Okay, once you get over the threshold voltage, and a typical silicon diode needs about 0.7 volts for forward conduction. But once you get over 0.7 volts, it acts just like a resistor. Okay, if you try going the other way though, if this side becomes positive and you try to flow those electrons against the arrowhead, nothing happens for a while. And here's a graph that describes it very well. So when I have a forward bias and my current's going in the forward direction, I got to get over that 0.7 volts. So that's what's going on right in here. And then once I get past the 0.7 volts, it's pretty kind of ish, sort of linear-ish. Okay, so it's acting pretty much under the influence of Ohm's law once you're conductive. Going the other way, however, if you get a reverse voltage on it, you don't have much current at all flowing in here. Okay, this can be microamps, this can be nanoamps. Very, very, very small currents. Until the voltage gets too high. And then you get the breakthrough. And this is generally when you let the smoke out of a typical diode. So it just can't hold the voltage back anymore. Current starts to flow, and then the whole thing breaks down. Now, there's all kinds of different diodes out there, folks. So the typical silicon diode, it's going to act just like this, and then it breaks. But there are also diodes called Zener diodes that are meant to work in the reverse direction. And those will become things like your constant voltage sources. So what you do is you intentionally run them backward, okay, and they'll hit this reverse breakdown, and they will allow enough current to flow to hold at 5 volts, 9 volts, whatever the case may be. I'm just going to back up. So where do you use these things? The big one, charging systems. So let's say I've got a solar panel and I've got a battery. I hook them up in a real simple system. When the sun's out and the voltage out of the panel is more than the battery voltage, current goes into the battery and it charges and everything's great. When the sun goes down, however, if I don't have something to stop that energy from flowing back into the panel, my solar panel becomes a giant resistance heater and I lose all my energy. Okay, so you always have diodes in charging systems. Rectifiers. Okay, diodes are super important when you want to turn AC into DC. And we're going to do a little demonstration of that. And lastly, I already told you about voltage regulators. And the last one is spike suppression. So if I want to switch a coil, and I go to turn that power off, I'm going to have this magnetic field that's flowing around the coil. If I suddenly turn the current off and I have a very high dIdt, what happens? Oh, you guys need coffee. Okay, if I have a very high dIdt around a coil, I end up with a very high induced voltage. So I can end up with a voltage spike that will kill my control system. Your diodes are capable of snubbing that and dissipating that energy as just thermal energy. So they're very important for that. And I'll show you how to implement that in a second. Okay, we went over this. Okay, here's how you use a diode to turn AC into DC. So we've got 3 phases of 3-phase power coming in here. And that is actually, I'm going to use a little model airplane motor. Typically, those are all just little 3-phase motors. So if you back drive them, they make 3-phase AC. 3-phase is nothing more than 3 AC waves 120 degrees apart. So every time the polarity changes, these diodes up here will either shunt the energy to the positive rail up here, the positive wire, or they're gonna shunt it to the negative down here, and they're gonna do all that switching automatically for me. Okay, I didn't have any compressed air in here, so I have to do the demonstration via video.
Hi students. Today I'd like to demonstrate AC rectification into DC through the use of switching diodes. In front of you, I have a small three-phase generator. This is just a model airplane motor that we're going to back drive and use as a voltage and current source. And this board has 6 diodes on it. Every time one of the phases of three-phase power changes polarity, these diodes will actively switch whether the current is shunted to the positive rail or the bottom ground rail. This is a capacitor that's going to store electricity so that it has a smoother or a filter and maintains a very quiet DC signal. Okay, so let's watch the oscilloscope and see what happens when I spin the rotor. Well, not much. And I'm barely getting any signal at all.
So it's actually below that 0.7 volt
Let's turn the motor a little bit
so I
faster.
wasn't getting
I just
any
happen to
forward.
have a little system for turning it faster. And that would be this gas turbine. This is a high pressure gas turbine. It has a Dale valve nozzle in here, and it can feed air at up to Mach 2 into the rotor. So let's hook up our oscilloscope and see what happens now.
Anything worth doing is worth overdoing.
Negative wire up. Hook the positive wire up. This one has a removable filter capacitor, so I'm just going to pull that out to begin with. But we have the exact same board. Okay, we'll turn the air on. And our rotor spins up. So now you can see the signal flashing by. And what I'm going to do is hit one stop. These are the peaks of each of the AC waves being generated by that little motor. Now this could be used just fine to charge a battery or something like that. But if we need really quiet DC power, I'll put my filtering capacitor in and let's take a look at the impact of this impact. So now when I run it, you can see that the capacitor is storing that charge and carrying the circuit through each of the AC waves.
Okay. I had way too much fun with that little thing. I accidentally turned it on to full shop air pressure one day, and I forgot to put the electrical load on it, and I looked down and it was turning over 50,000 RPM. And it still held together, which was quite amazing. I wanted to do a department challenge and have you guys build those things. And we were going to see who could build the most efficient turbine. Because, you know, Pratt & Whitney is a major contributor to the university. So I was going to have some of their engineers come up and check it out. If you think something like that would be cool, contact your MSAC rep, and I'll try and set it up for next year. Unfortunately, you guys will be all off making big money, so you don't get to play with toys. Okay, so again, for small currents, okay, let's say I have a 2-volt battery, and this is my positive lead. I come out and I go through a 100 ohm resistor, down through my diode, and back. I gotta account for that 0.7 volt drop across the diode before I do ohm swap. So for this circuit, I'm gonna end up with 13 milliamps. So just watch your voltage drops. Okay, of course, there's all kinds of variations. We got LEDs. They're the exact same thing. I could take and actually swap out the diodes in this, and I could have had it flashing with every single AC wave. Okay. Typically, your LEDs aren't going to be happy carrying the current that a typical silicon diode is going to be happy with. But they would do it. Always, if you're going to run an LED, make sure you put a current limiting diode in there, something in the 500 to 1,000 ohm range. Don't want to overheat it. Okay, linear voltage regulator. I mentioned Zener diodes before. Okay, this thing is nothing more than a packaged up Zener diode. So the Zener is reverse biased, and it's going to flow enough current so that we get, in this case, a regulated 9-volt output. No matter whether we put 10.5 volts or up to 35 volts. Now, if I run higher voltages here, let's say I run 35 volts, this thing is going to get raging hot because it's holding a lot of current there. Okay, so you've got to heat sink it. These regulators, they work, they're convenient, they're nice, they're not very efficient, but they are very easy. So if you're just making something like the Arduino demonstrator board by hand, yeah, these work great. Would I ever use these for, I don't know, a laser power supply where I needed 500 watts? Heck no. I'd use a switching power supply. I would do some other topology. Okay. But again, this is a packaged diode. And that's all you need to know about diodes. That has gotten me by for the last 35 years. Just remember, diode, check valve. It lets current go in one direction with a small voltage drop, and it can block many, many volts and large currents going the other way. Okay, transistors. This is where it really gets cool. If I have a microcontroller, okay, like a processor on this Arduino board, you know, I can get maybe 40 milliamps through it. Maybe I might push it to 100 for a very, very short period of time, but things are going to get hot. Okay, you cannot get a lot of power through a microcontroller. They're not made for it. But what you can do, however, is you can use something called a power MOSFET, and these things will handle hundreds of amps. You can put huge power through these things. Okay? There's multiple types of transistors out there. I'm going to totally skip what we call BJTs, bipolar junction transistors. BJTs were the original transistors that were developed by Bell Labs back in 1948. The problem with them, though, was that they were current-controlled devices. Okay? And if you have something like an Intel microprocessor chip, if that were all driven by currents, it would get so hot that it would cook itself. These things are all run just by voltage, by the electric field running through a semiconductor, and that makes these things act like a voltage-controlled resistor. So I can make this thing either fully on or fully off. When this thing is fully off, and I were to measure the resistance between this first pin called the gate and this one called the source, you have millions and millions and millions of ohms. Okay, it is off hard. Depending on the device I select, if I put 5 volts on the gate and I ground the source, that could go down to as low as maybe 1 milliohm. It becomes almost as conductive as a piece of copper wire. Okay. All you really need to know, these things are voltage controlled resistors, and they can take a lot of power if you properly heat sink them. You get rid of the heat so they don't fail. Okay. They only do DC, they don't do AC. There are AC variants of this thing, they're called triacs. Okay. We're not going to bother with those in 50 minutes. Okay, so triac for AC. So the transistors themselves, they come in basically 4 flavors. There's N channel, P channel, and then there's enhancement mode and depletion mode. Okay, Professor Sheaf would probably cringe when I say this. All you really need to know, N channel, it switches the negative wire. So if you want to do low side or negative wire switching, grab an N channel. And then if you want enhancement mode, it's normally off. If you choose N channel and depletion mode, it's normally on. So by applying voltage to the gate, you'll flip it to the opposite state. P channel. Okay, P channel is your high side switching. You're switching the positive wire. And we'll go through how that works. These things come in all kinds of different packages and sizes. Okay, this is called a TO220 package. It's a good mid-range kind of transistor. And I've got one hooked up right here. So I've got my Arduino. And what this is going to do, this is set up for low side switching. So I'm going to switch the negative wire. I'm going to attach 12 volts. So right now I've got 12 volts going into this Jeep headlight. And then I'm going to use PWM to switch the gate on the negative wire. So by modulating the PWM going to the gate, I can make that light brighter or dimmer. And right now, typically, when I do this kind of thing, this Jeep headlight probably has, it's got like 2.5, 3 amps going through it, and 12 volts. Okay, that's the other thing. If you need to switch a higher voltage, you can absolutely do that. So my 5 volt control signal can control a 12 volt load. That's absolutely fine. So to make it go, the gate, that's your control pin. And your control is by putting your 5 volts across the gate and the source. So you're creating an electric field by putting that voltage in place. One of the key features of a MOSFET, folks, is that the gate is glass insulated. So you do not get any real current flow going into the gate. But that leads to another problem that you can run into. So if I just were to put 5 volts on the pin with my Arduino, and I didn't give that gate any way to discharge, okay, it's going to stay on. It's going to stay on like a charged capacitor. Ask me how I know. I burned up my capstone project doing that. I looked at it and said, yeah, you don't need that resistor going from gate to ground. Well, yeah, you do. Okay. And that capacitance created by the glass between the gate and the source, that's called your Miller capacitance. Okay, that's going to limit how fast this thing can turn on and turn off. But it also does something else. When we start doing really fast switching, okay, and by fast I mean 100 kilohertz, I mean really fast. The faster I switch, the more that capacitance gives a conduction pathway from the power side back into the control side. So if I switch too fast, and I'm allowing that energy to get conducted back into my controller, I can blow up my microprocessor. Okay, that's why we always optically isolate the control side from the power side. So that when we start switching really fast, nothing can come back over a light beam. It just doesn't happen. Okay? But if I'm only isolated by a capacitance, yeah, it can come back. Okay, so how do we make it go? Here's the basic wiring, folks. And this is that. So if I take, and I've got some battery, I've got the positive lead, I come up, I go to, say, I don't know, a volt, the G-head level. I'm going to use this symbol for my MOSFET. This is the generic FET symbol. Okay, I could be cool and I could have all the specific ones. There are symbols for N channel, P channel, depletion enhancement, all that stuff. But if I come along and I put 5 volts right here, and I have, say, 100 ohm resistor here going into my gate, now I've got 5 volts between my gate and my source pin, which is attached to ground, the negative wire back to the battery. Okay. I need both of these resistors, folks. The 10K is giving me the path to discharge the gate, to turn that Miller capacitance off, bring it back down to 0. The 100 ohm resistor, what this is doing is it's stopping inrush current that can also kill my controller. You know, when you're hooking up your laptop and you plug in your power supply for your laptop, you know how there's that big kind of spark that jumps when you plug it into the wall? Okay, this is preventing that same thing. So when the Arduino goes to charge up that Miller capacitance, if you don't have that 100 ohm resistor in there, it could charge so fast that it's going to pull too much current through the microprocessor and actually kill it. Okay, so this is just limiting the current that can come out of the microprocessor. Be a little more gentle. So 5 volts is on, this thing becomes conductive, and then big power and voltage can flow through my bulb. Exact same circuit, but if I take the 5 volts away, then my MOSFET now goes back to that millions of ohms, and everything shuts off. Let's make a change, however. Let's say this is a little DC motor, or maybe it's a solenoid coil. Okay, you must have a spike absorbing diode in there. Because when I turn that coil off and the magnetic field collapses at the speed of light, I can get hundreds of volts going in the opposite direction coming off that coil. That diode then gives it a path back. I establish a conduction loop right here, and then I can dissipate all that energy as heat, and everybody's happy. Okay. And this happens with DC motors too. As soon as they rotate, when the brushes come out of contact with the coil on the rotor, again, that magnetic field is collapsing, and you get all kinds of bad, noisy voltage spikes. That diode takes care of it, so you don't cook your microprocessor. Okay, so the first one was N-channel enhancement. Okay. So that means normally off N-channel low side switching. This is the low side I'm talking about. It's attached to the negative wire, the low potential side. If I go to depletion, now when I put 5 volts on the gate, it's off. So that's a normally off switch. And when I take 5 volts away on a depletion transistor, the light comes on. Okay, so I told you there's 2 types of transistors. There's N-channel and P-channel. Now we're going to do high side switching. So we're going to switch on the positive side of our load. So this is our electrical load that we're driving. Okay, the P-channel, first off, they're not as common. They're also not as efficient. So with an N-channel, you have extra electrons in the valence shell in the crystals, and that makes things nice and conductive. You know, you got these electrons, you just push them along with an electric field, everything's great. P-channel conducts by holes in the valence shell. Okay, they are simply, by nature, not as conductive. Okay, they're good. Okay, but maybe the P-channels are going to give you like 0.1 ohm in the on state, whereas your N channels will be down to the 0.0 something ohms. So your N channels are like a factor of 10 more conductive, but they're both really good. Okay, for P channel, the big thing about the P channel is that you turn it on with the gate, just like the N channel, and you reference from gate to source, and your source is up on the high side rail, on the positive wire. And when you look at P-type transistors, they're always going to say a negative voltage to turn it on. So you'll see that you want to go from, say, this 12-volt rail, maybe you want to go minus 5 volts to make it conductive. So that means, well, okay, let me run with this. Let's say I'm going to put 6 volts on the gate to turn it on. I have to come from 12 volts down to 6 volts. So this would be a minus 6 volts gate to source. Kind of a pain in the butt. So in order to get that, what I do is I'll have some kind of a switch down here. This could be a physical switch. It might be another transistor. So I might put an N channel down here to make this go. why am I doing all this? That sounds really painful. Okay? Well, a simple one that we can relate to as Becky's, you got something like this, car driving light. One wire. The negative wire on this thing is through the grounding plug on the driving light. I don't have a negative wire. So if I want to light this thing up, I've got to switch the positive wire. Okay, that's an obvious example. There's other stuff. These are used in bipolar amplifiers. There's all kinds of other stuff you use it for. But that's a very simple example. I've also had some times where I was building a solar battery charger, a charge control system. I had to switch the positive wire, and P channel was just the way to go. Also, you know, maybe I want to put in a shunt resistor down here and measure the current. Okay. You don't want to have a shunt resistor and an N channel together, because then your gate will be above the value of the shunt resistor. It gets complicated. Okay. So if you don't have access to the negative wire, do high side switching. But just remember, you are bringing the gate down from the high voltage bus. So high side switching. Already hammered through all of that, so that's good. Okay, so now that you saw those other slides, this is a great video. It made my head swim a little bit even when I was watching it, because they talk about VGS, which is the voltage gate to source, and how you turn things on and its negative voltages. Now that you understand what it's referring to, so N channel, you're referencing ground. P channel, you reference the high supply side, the high voltage side. Why don't we come back to this one? This is a fairly long video. It's really good. But we'll come back to that depending on, you know, we have 13 minutes left.
Sponsored?
Okay, so let's do some examples. So I just went to the DigiKey catalog to show you what kind of stats you can get on these. This thing has a slightly larger case. Okay, this little one I'm turning the headlight on, that's a TO220 case. Be careful, guys. Okay, TO220 case, that shape is used by a lot of different devices. Okay, so just because it looks like that, don't just assume it's a transistor. You could have a voltage regulator in a TO220 case. You could have a diode in a TO220 case. Okay, be careful. Don't just look. Make sure you check the part number. Okay, but this thing right here, for $5.30, if I keep this thing at 25C, and that's a big if, I can put 195 amps through that thing. Okay. That's a big if. Okay. Professor Segee from the electrical department, he used to tell me, he said, Steve, electronics aren't hot unless you touch them and it leaves skin behind on the device. That is not a good way to test things. I said, Bruce, come on. Okay. So do not run them that hot. I think for TO220, the maximum temperature is 175 C. So they run hot. Most electronics, if you can keep your hand on it, it's just fine. Okay. So 195 amps and 1.7 milliohm. I can't tell you how jealous I am. when I was in your chairs, we never saw things like 1.7 milliohm. We jumped up and down if we were in like the 0.1 ohm range. And then of course you gotta get rid of that heat. So you're gonna need something like a heat sink. This is one of the heat sinks that I use for the big transistors in Crosby. Okay, this thing will just about cool off global warming. When we were doing autonomous land drones, I had the students build their own motor drives, and this is what was cooling down the transistors. Okay, so if you're going to do any kind of design of motor drives, transistor drives, stuff like that, conceptually, it's really easy. Okay, just go back to your old heat transfer days. So the power that you're going to get rid of, Q dot, and that should be a dot, is just the stack of thermal resistances times the temperature rise. And Q is going to be your running current squared in your device times the device resistance in the on state. Okay? I don't want to figure all that out. So what I actually did was I made a Google sheet and I posted all this for you guys. So if you should ever need to do this for whatever reason, you can actually come in here, change all of these inputs with all the stuff off your data sheet and what your running current's going to be. And you can look at how that device is going to heat up. So this one, I would not expect this device to go more than maybe 50 C in operation running a G heavyweight. That's a pretty low value. Okay. And this is actually that transistor. So if you need it as part of your experiment, I keep these on hand. Okay, we got 8 minutes left. I think that is the last slide. Guys, that was like really fast. It's simple stuff, but I know it's new. Are there any questions? Did I rock anybody's world or make you go to sleep? All right. Let's see how far we get with that cool video, because it's really good.
Sponsored by Brew. This is a MOSFET. Inside, there's just a tiny piece of semiconductor. But these components are so important that we find them everywhere. MOSFETs look something like this. They come in many shapes and sizes. They are represented with symbols like these in engineering drawings. I'll explain those later in the video. MOSFETs have 3 hidden terminals. We call them the gate, drain, and source. Sometimes these terminals are in a different order, but you can check that on the manufacturer's data sheet. And you can find that online using the part number which is printed on the front of the component. I want you to imagine water flowing through a pipe. We can block the flow with a disc. There is a hole on one side of the disc, so if we slide the disc across, we can let water flow again. The disc is spring-loaded, and so it is normally closed. Another pipe connects to this disc. The pipe is filled with water. If a small pressure is applied to this pipe, it won't be enough to move the heavy disc, but at a certain pressure, the disc will begin to move and allow the water to flow. As we increase the pressure, the disc fully slides across and the water can fully flow. But if we remove the pressure, the gate closes and the flow of water stops. This is basically how the MOSFET works. If we take a lamp and we connect it to a power supply, it will turn on. If we insert a switch, we can manually control this. If we insert a MOSFET between the drain and source pins, the lamp will remain off until we apply a voltage to the gate pin. And that means we can use a controller or sensor to turn the lamp on automatically. But if we vary the voltage on the gate pin, we can vary the current flowing through the main circuit. And that means we can also dim the lamp as well as turning it on and off automatically. Instead of a lamp, we could control a relay, and a relay can control an AC circuit. And that means we can turn an appliance on and off automatically and even remotely. We could also control the speed of a DC motor. The motor can rotate forwards or backwards depending on how we connect the power supply. But using MOSFETs, we can automate and change the direction. Some electrical loads have a high current, which causes the MOSFET to heat up. So we attach a heatsink, which increases the surface area with the air and helps to cool it down. For example, this DC power supply uses MOSFETs. The MOSFETs are attached to some very large heat sinks. Without them, they quickly rise in temperature. We can turn MOSFETs on and off extremely fast by using a pulse width modulation signal. That lets us efficiently control the brightness of an LED light. We have an entire tutorial on how to design and build that circuit, links down below for that. Okay, but why can't we just use a transistor? Well, a BJT transistor requires current to be applied to the base bin, and that wastes energy. A MOSFET only needs voltage, and almost no current flows. So the circuit is more efficient, easier to design. MOSFETs can also handle much more current. These larger versions are through-hole type. We use them on test boards, but also PCBs. These smaller versions are surface mount type, and we use these in compact electronics. These multi-pin versions are just multiple MOSFETs combining together, but typically there is just one MOSFET per device. Try and build this circuit yourself. Take a 9-volt battery and connect it to one side of a lamp. Connect the other side to the drain pin of the MOSFET. Then connect the source to ground. Take another wire and connect this to the gate. Your circuit should look something like this. Notice that the lamp is on, but if we connect the gate wire to the 9-volt supply, it will activate the MOSFET and the lamp turns on. Current is flowing through the circuit like this. Now, if we disconnect the voltage to the gate pin, the lamp remains on. And that's because the MOSFET is now stuck. The gate terminal
That's how I think my capstone.
which stores charge. If this charge has nowhere to go, then the MOSFET will remain activated. We can discharge the terminal by providing an exit to ground, which will deactivate the MOSFET. When the MOSFET is fully on, no current flows on the gate terminal. But when the MOSFET is changing from off to on, electrons rush into this terminal for a split second. And so there is a large inrush current flowing here. If you are using something like an Arduino to power the MOSFET, the current passing through could damage or destroy the board. So we need to add a resistor to the gate pin to limit the current. To discharge the MOSFET, we need a path to ground. Now, we can't use just a wire, because too much current will flow. So we place a high value resistor here. When the Arduino energizes the gate pin, a small current will flow through the resistor, but the MOSFET gate pin receives the full voltage. When the pin is de-energized, the stored electrons can escape down to ground. If we place the resistor on the right-hand side, then we will create a voltage divider. So less voltage will be provided to the MOSFET gate pin. For this reason, the left side is often preferred. For the next circuit, we again connect a 9-volt battery to the lamp, and then the lamp connects to the drain terminal. Then we connect the source to ground. Then we connect the battery to a resistor, and then to a potentiometer. We connect the end of the potentiometer to ground, and we connect the center terminal to the gate pin. The circuit should look something like this. The MOSFET will be activated, so the lamp turns on. The resistance is so high here that almost no current flows through the resistor. We just get a voltage. When we disconnect the power to the resistor, the MOSFET drains through the potentiometer. If we apply the voltage again, we can rotate the potentiometer to increase the resistance. That reduces the voltage available at the gate. As the gate voltage reduces, the MOSFET begins to deactivate, increasing the resistance between the drain and source. And so the lamp becomes dimmer and dimmer until the MOSFET completely deactivates and the current is blocked. So we can turn the circuit on and off, or we can vary the gate voltage to vary the resistance. We do also have a full tutorial on potentiometers, links down below. And you can also find links to on mugs and help support the channel. We have two main types of MOSFET, the enhancement and the depletion type. Enhancement is the big on.
Okay, guys, we're at time for class. If you need to leave, that's fine. This is about halfway through. There's still some good stuff, and we have the roadmap to this. So if you want to keep watching, I'll let it play until the end.